Okay, so in Chapter 7, we're going to be getting into what's called the continuous probability. And because of time and in terms of applications, I'm going to limit our focus in this chapter to basically talking about what is called the normal curve. And the normal curve basically looks kind of like your bell-shaped curve. And we're going to basically spend the entire chapter just talking about how to work these type of problems. And then you'll find that basically everything after Chapter 7 and dealing with the probabilities all basically deal with the characteristics of the bell-shaped curve. So that's going to be our limit in terms of volume, in terms of content for this particular chapter. And just, some characteristics of the normal curve. Obviously, I just drew a picture of it. It is a bell-shaped curve. It is symmetrical. Just a couple big things. Down here, notice the mean, the median, and the mode are all equal. And basically the total area under the curve is defined to be 1 or 100%. So again, if I were to draw the curve again, so here's my curve, and so obviously we're going to start off later on, we're always going to put the mean, which we're going to call mu, in the middle. But what they're saying for this one is basically everything under the curve is 1 or 100%. And our issue is going to be finding areas, particular areas under the curve. And I'm going to try to give you visuals in terms of what we're going to be looking for. And just kind of remember, the thing about a normal distribution is that x will never equal exactly anything. And so the idea is because it's continuous, we're always going to be looking for a range of values under the curve. So as you can see by this example, notice the mean and the median go right in the middle of the curve. And just to kind of make some more notes, remember the thing that this thing is symmetrical, that basically each half is the same. So you could basically say each half is said to be 50-50. Now, one of the things we're going to be getting into, in order to use the bell-shaped curve or the normal curve, we're going to have to get or calculate what is called a z-value. So everything under the curve is said to represent what's called a z-value, which simply represents how many standard deviations x is from the mean. So if the mean is going to go in the middle, and we're going to define that as letter mu, that's the Greek symbol for mu, that's your mean, what we're going to basically do is this calculation right down here, where we take x, which is going to be your variable, minus the mean, divide by sigma. Guys, sigma is basically your standard deviation, which typically will be given in the problem. Once we do this calculation, this z-value is what we're basically going to be using to actually look up in the probability tables to calculate the area or probability under the curve. So get used to it. We're going to be talking about what's called the z-value. Now, you'll find this table in the back of your book or in your appendix, and basically here is what your table of probabilities of z look like. And notice you're going to have a z-value out here, and notice you've got in this column you have a series of z-values. Notice in the upper row of this table you've got your z-values out to the 100th. So for example, if you wanted to find a z-value that's equal to, let's say, 1.31, you'd go to 1.3, and then where that intersects with 0.01, guys, this area would be the area you'd be looking for. So if I were to draw the curve, and let's say, okay, in the middle, there's 0, because you're always at 0 right in the middle, and let's say that 1.31 was right there. If I were to say, guys, give me the area between 0 and a z-value of 1.31, you'd go to your table, you'd find 1.31, you'd see, oh, it says 0.4049, guys, and that would be how you would calculate the area from 0 to 1.31. Now, in this particular example, they're saying, what if you had a z-value of 1.5? Well, that's pretty easy. Again, 0's in the middle, and 1.5.0 is right there. So this number right here, 0.4332, would be defined as the area from 0 all the way up to this value right here, which is your z-score. So this area is said to be 0.4332. And by the way, area also means probability. And just to kind of keep going, and they do this in your textbook, so for example, if you had a z-score that's 1.0, obviously if you go into your table, you're going to find that from, for example, I'm going to give you a better visual here. So let's say you had 0 and you went up to 1. Again, I'm going to draw my lines here. If you were to go to your table would give you an area that says 0.3413. So essentially, let's say you wanted to go down to a -1, which is exactly the other side of the curve, guys, that would be another 0.3413. So basically from 0 to 1 or 0 to -1 is really defined as the same probability. So up here where they're saying multiply this times 2, that's basically what they're saying is you're applying symmetry because both sides are the same. So any area that's between a -1 and a +1 is simply this particular area multiplied by 2. And you can do the same thing for a z-score of 2, a z-score of 3. If you're looking for plus or minus 2 or plus or minus 3, that's how you basically get the area. So again, in this example, they're showing you what you'd have to do in terms of the steps to calculate a z-value. And notice that they give you the mean value, to be 1,000. They give you sigma, or standard deviation, to be 100. And then it says, what is the z-value for the income, let's call X, of a foreman who earns $1,100 per week, and then it says for a foreman who earns $900 per week. And so what they're basically saying before you could do that, or to get the actual z-score, is you just plug it into the formula. So up here you take 1,100, which is X, minus 1,000, which is mu, divide by sigma, which is 100, and of course you get a z-score that's equal to 1. And then the same thing if you did it for 900, it's the same thing. 900 minus the mean, which is 1,000, divide by 100, which is the standard deviation. In this case, you would actually get a -1 z-score. So again, that's how you calculate z. So in this particular illustration, they're wanting you to find the area from 1,000 all the way up to 1,100. Now remember, 1,000 is defined as mu, so by definition, that's going to have a z-value of 0. Now, we already calculated this previously, but to get this z-score, remember, it's going to be 1,100. You subtract out the mean, which is 1,000. There's 100. Divide by the standard deviation, which is 100. And obviously, you're going to get a z-score that's equal to 1. So basically, you're trying to find the area between 0 and 1, because they're saying, what is the likelihood that a selected foreman whose weekly income is between $1,000 and $1,100? So basically, we know we're at 0. We got 1, so really we simply go to the table and we can look up a z-score that's equal to 1, and that table will give you the area from 0 to 1, and you're going to find that's going to be 0.3413, and that should be your answer, and that's what's going to show up on the next slide. So again, so here it is. So once we've got that z-score equal to 1, notice you would go to your z-table. You go down here, you locate 1, and here's the area they give it to you, which is 0.3413, and by definition that gives you from 0 to 1, and that just happens to be what we're looking for, so that is your answer. Now in this illustration, you're trying to find the area between the income that's right at $790 and 1,000. Now remember, 1,000 is still your mean, so that's going to have a z-score that's 0. 790 has to be converted into a z-score, so they did that right up here. Okay, so don't worry about this letter S. That's the sample standard deviation, but for now, just make sure you know that that's just a standard deviation for this purpose. So if you took 790 minus the mean of 1,000 divided by 100, you get a z-score that in this case it's a -2.10. Now remember the idea of symmetry. Let me just kind of, in case you're getting confused at this point. So if we're at 0, and we're looking at a -2.1 z-score, remember, if we were looking on the other side of the curve for a +2.1, okay, the way the table works is 0 all the way up to a +2.1 versus 0 down to a -2.1 is exactly the same. So all you really have to do is, don't worry about it being negative. You'll just go to your z-table, look up the absolute number for 2.1, which in this case, 2.1, I look it up, it's going to be 0.4821. Guys, that's basically going to be that basically represents from 0 to 2.1, which also is going to be the same area for 0 to -2.1. So if you look down here, that's basically your area, and because it's given, that's also going to be your answer, which is 0.4821. Okay, so in this example, they're wanting you to find the area that is actually less than $790. So remember, when we converted 790 into a z-score, we got a -2.1. So if I were to draw my curve, and of course, zero's in the middle, we've got negative 2.1 right here. Let me draw my line. They're basically wanting you to find that part of the curve. So obviously, if you went to your table, and like we just did in the previous example, we figured out that 0 down to a negative 2.1 was right at 0.4821, okay? Now, basically, we just have to fill in the hole. We have to figure out the rest of the 50% because remember, we're just looking at half the curve. So in order to find this lower part of the curve, all you do is you take 50% and you subtract out that 0.4821, and then that's going to give you 0.0179, and that's basically what they're showing you right there. So the answer would be 0.0179. Okay, so another illustration, you're trying to find a couple numbers under the curve, an area under the curve. And so they want us to find between $840 and $1,200. So notice right away, 1,000 is still in the middle. There's your mean. And you've got to convert $840 and $1,200 into z-scores. And so right up here, here's your calculation. 840 minus 1,000 divided by 100 is going to give you a negative 1.6. That's your z-score. You take 1,200 minus 1,000 divided by 100. You're going to get a positive 2, guys. That's going to be that z-score. So basically, you're looking between these two z values. You've got a negative 1.6. That's that z-score. And you've got a positive 2, which is basically that z-score. So remember, you just have to look up the absolute numbers. So if you go to your z-table and you look up 1.6, remember that's going to give you 0 to 1.6, which is the same as 0 to negative 1.6. So just look up 1.6. You're going to find the answer there is 0.4452. If you also then go to your z-table and look up a positive 2, it's going to give you an area that's 0.4772. And so basically the final answer would basically be you have to combine these or add these together to basically get the whole area under this curve in terms of what you're looking for. Okay, so in this illustration, you're trying to find the area between 1,150 and 1,250. So if you look here under your curve, notice you got 1,000 is still your mean. There's your mu, that's in the middle. Here's your 1,150, and here's your 1,250. So you first have to convert these to z-scores. So you take 1,250 minus 1,000 divided by 100. There's your first z-score, which is 2.5. You take 1,150 minus 1,000 divided by 100. You get a z-score that is at 1.5. Okay, so now we're trying to find, again, I'll kind of write this in red, this particular area. So if you look up a 2.5 z value in your table, you're going to get an area that says 0.4938. If you look up 1.5, you're going to get an area that says 0.4332. All right, now remember, these are cumulative areas from 0 to 2.5 and 0 to 1.5. So to get the intersection, to get what's in the middle of these two, you basically just subtract, and your final answer is going to be 0.0606. Now, sometimes you're going to be giving a problem that you're going to be given some unknowns where you're going to know a z value, but they're going to make you work backwards to solve for x. So anytime you got to do a problem like this, I just like to go back to the simple formula and just to kind of remind you that the actual formula to calculate a z-score is x, okay, minus mu divided by sigma. So what will happen is basically you'll be given the z-score, you'll be given the mu value, and you'll be given the sigma, and then you'll basically just have to use some basic algebra to plug it into this equation to back into x, which is going to be your unknown. So what will happen is to get the z-score, they typically like to give you some sort of percent or some sort of area. Like in this particular problem, it says they want to set a minimum guaranteed mileage so that no more than 4% of the tires will have to be replaced. So the idea here is we can go to the table and use that 4%. I'm going to write this as 0.04. We can use that as an area and try to then locate a z value. Once we can use this percent, which is an area, to locate the z value, notice we've got the mean, we've got the standard deviation. We can then plug in whatever z-score is associated with this 4% into this equation to solve for x. All right, so to locate a z-value, we may have to actually approximate it because we might not be able to find the actual percent. So if you look at this particular area, notice we've got 4% roped off here. That's a minimum number, so minimum is the lower part of the curve. We're trying to find a z-score that's going to be right about there, right? So we know that if 0 is in the middle, 0 down to this z-score, and we know that this area is 0.04, if you just use the complement rule, guys, we know that 50% minus 4% would give you 46%, okay? So what you need to be looking up in your table is actually 50% minus 4%. So we're trying to find approximately from 0 to this point about 46%. So if you go to your z table, notice we don't see 0.46, but guys, 0.4599 is a pretty good candidate. That's close enough, so we're just going to approximate it. And so the z-score that's associated with about 0.46 is 1.75, and that's going to be a negative because it's in the lower part of the curve. So we're going to say the approximate z-score is a negative 1.75 because we know if we go from 0 to about negative 1.75, we know that that takes up 46% of this part of the curve, which we're trying to find this part of the curve, which is the other 4%. But it doesn't matter. Whether you're at 46% or 4%, it's still the same z-score. So we're going to be using negative 1.75. So if we go back to this equation, you simply plug it in. You've got a negative 1.75 equals, we're going to solve for x minus the mean, which was at 67.9, divided by the standard deviation, which was 2050. And at that point, you just do the math, cross multiply, take 2050 times negative 1.75, and then you're going to add over the 67.9. You're going to find that x is then going to be equal to 64,312. Okay, now you're going to find that there's another application with the normal curve in that you can actually use a normal approximation curve to approximate a binomial as long as the sample size is large enough. So typically there's a test you do, and again, I know that the textbook uses this. I like to use the letter P, so NP or n times 1 minus p, because I don't want you guys to get confused by the pi symbol thinking that's 3.14, which it is not. But the basic rule is if you do a simple test, if you take the n, the number of trials times the probability of success, if that's greater than 5, and n times 1 minus p is also greater than 5, which by definition they both will be, then you could say that the sample is large enough that you don't actually have to use the binomial tables. You can actually use the bell-shaped curve to approximate binomials. Now, the problem is going to be because binomials are discrete and the bell-shaped curve is continuous, we have to kind of factor in the fact that we can't say x is ever equal to anything, so we have to come up with a range of values. So in the next couple slides, we're going to talk about this thing called the correction factor, which is 0.5. The correction factor is going to basically give us an adjustment to approximate a range of binomial outcomes. Okay, and so like I mentioned before, the correction factor is the number we're going to be using. The value is 0.5, and you're either going to add or subtract it to your x value to actually develop your range. So, depending on what you're looking for, we'll set up the bell-shaped curve. We'll graph or we'll plot the data points, the range we're trying to find. And what's going to happen is a little simple rule to remember is if you get comfortable with drawing the bell-shaped curve visual, I always tell my in-class students that an easy way to remember when to add or when to subtract the 0.5 is once you draw your picture, you always want the 0.5 to be either added or subtracted to the value that you want to be just outside of the range. So regardless of what your picture looks like, if this is our range, for this particular value, we're going to do a plus 0.5, and for this particular value, we do a negative 0.5, and then you convert to z. So this 0.5, typically, if you get, an easy way to do it is to draw a curve, and regardless of where you're at, any particular area you're trying to locate under the curve, you always want to be just outside of the area. You never want to be within the area with the 0.5. So you'd always either add 0.5 to that number or subtract 0.5 to that number to come up with the actual values you're going to use to convert to z. And that's simply the one thing you got to apply using this thing called the continuity correction factor. Now, if you don't like to draw the curve and you'd rather just follow a specific set of rules, you can go over this scenario, in terms of when to add or when to subtract the 0.5 for the probability that if you're talking about an at least idea, that's a greater than type of error. They're saying you subtract 0.5. If it's more than x, it's the area above, you do a plus 0.5. If it's x or fewer, it's going to be below, it's going to be a minus 0.5. And if it's fewer than x, it's going to be an area below, you do a plus 0.5. Again, I think sometimes if you try to get into just memorizing these, it can actually make it more confusing, which is why, again, if you just simply draw your curve, you locate what data points you're looking for. In fact, it might even be something like this. You might only be going one direction. If we're going to the right, we would be subtracting 0.5, all right? If we were going, for example, to the left, let's say just to the left, we're going to add 0.5 because we want to be always just outside of that area. So again, I'm not trying to confuse you. I hope if you go by visual, sometimes it's easier to remember than just trying to go over these rules. And of course, I'll give you some other illustrations when we get to the applications of how to actually do it. So notice in this case, we're going to do a binomial application. And if I look down here at the bold, notice they're wanting the probability that 60 or more will return for another meal. Okay. So again, in a moment, I'm going to draw the curve, but it says 60 or more. So I'm thinking we're going to be going to the right. So right away, if I were to kind of just visualize something, I'll just kind of draw a line. 60 or more, meaning we're going to be looking somewhere to the right. I'm thinking right now, whatever value we're going to do is we're going to be subtracting 0.5 because we want the number to be just outside of that area. So notice if we did our test, obviously if you took n times p, we would get 56. That's more than 5. And np times 1 minus p, same thing, you're going to get more than 5. So this would meet the criteria that the sample is large enough to use the binomial application. And then, of course, to get the standard deviation, we just take the square root of 16. We got about 4.10. Okay. Now, so if the mean is 56, let me just kind of just start this thing from the beginning. So we could basically put 56 in the middle because that's n times p. And the question says we want 60 or more. And if you just kind of follow my visual, all you got to do is subtract 0.5 because when we want to be just outside of that range. So technically, we're going to be using 59.5 for x, and we're going to convert that into a z-score and then get the area. So basically, if you look up here, you're thinking, okay, why are they doing 59.5? It's basically you start with 60 and you want 60 or more. So basically just subtract 0.5 to get you out of that area. So 59.5 minus the mean divided by the standard deviation gives you a z-score that's right at 0.85. And so at that point, you go to your z-table. 0 to 0.85 gives you an area of 0.3023. You subtract that from 50%, and your answer is going to be 0.1977.